Alright, so in this video, I want to continue my discussion on vectors. And in this particular video, what we'll talk about with vectors is to sort of look at one vector and, and the kind of vector that we're looking at is one in which we already know the x and y components of in a particular coordinate frame. And what we want to do is use the information that we have about the x and y components in that coordinate frame to find the x and y components of that very same vector in a different coordinate system that bears some relationship to that original coordinate system. So that means that if I have a coordinate system like this, with normal x and y-axis, and I have a vector which we'll call A, and we have the y and x components as normal. In this case, we already know what the vector components are in this coordinate system. However, if we look at it at this very same vector in another coordinate system, the only difference being that that new coordinate system is slightly rotated. There's a slightly rotated version of this original coordinate system. So if I were to draw it in another color, maybe blue, and I was to draw it like this, something like this, right? And in this case, I'll call this coordinate y prime, and I'll call this x prime. Now this very same vector, we haven't changed it at all. Now we're looking at it in this coordinate frame. We're assuming that we already know what ax and ay are in the original coordinate system that's given in white. And this new coordinate system, this blue one, we know what the angle at which it's rotated from the original coordinate system. And we'll call that theta. It's just slightly rotated, but otherwise it's exactly the same thing. And we know this angle of rotation. So using this angle of rotation and these original components, we want to find a of x prime and a of y prime. This would be a of x prime. And this would be a of y prime in this new coordinate system. So once again, I'll just recap to make it extraordinarily clear that what we want to do now is to find the x and y components of this very same vector in a new coordinate system that's slightly rotated from this original coordinate system, using the information we already know about this vector in the original coordinate system. So if we write out the vector A, we know that we can represent it two different ways. We can represent it as a of x in the y direction, right? Because this is the unit vector for I plus a of y in the j direction, because that's the unit vector for j right there. But we can also represent it as a of x prime times I prime, because now in this new coordinate system we have a unit vector along the x prime vector, which will x prime coordinate, which we'll call I prime plus a of y prime j prime, because now we have this j prime along here. So now my job here is to basically find out what, using this information, what a of x prime and a of y prime are. So it would be helpful to understand what I prime and j prime are in terms of I and j, because we can find that out quite easily. So if we wanted to find out what I prime is, which is the vector here along this, the x prime coordinate, well, you can see that this is a vector that has two components on its own. And maybe I'll use a different color just to highlight them more clearly. Right, so this I prime unit vector has a y component and an x component. Sorry, an x and a y component. Now this x component is I times the cosine of this angle. Times the cosine of theta. And the y component is j times sine of theta. Because we have this angle of rotation, I and j are right here. They're essentially equal to 1 on the coordinate system. They'd be located at point 1. So at the point 1 on the x and y coordinates. So really this new vector here has this vertical component, which this thing running along here is really equal to j times sine of theta. If you take a minute to look at that, you can see through SOHCAHTOA that that makes a lot of sense. And this horizontal component is essentially I times cosine of theta. So now the next step is to find j prime. And j prime is here. And now we can see that j prime is slightly different. It's this vector. So this vector, if you look at it, if you could sort of tilt your head a little and kind of look at the vector, it has this component and it has this component right here. Now this component, which is the vertical component, is equal to j times cosine of theta. That's this vertical component, and this horizontal component is negative I times sine of theta. You can see that because along this x, this is the negative x-axis, you'd have negative I running along it. Kind of like how I is running along the positive x-axis. So this is negative I. I should make this x a little bit more clear. Okay, so negative I is running along here, and that's theta. So since the x component of this j prime vector is in the negative x-axis, it's in the negative quadrant, the negative x, the quadrant where x would be negative, we know that the horizontal component is obviously negative. So that component is negative, and it's negative I times sine of theta, because negative I, this unit vector, times the sine of this angle, theta. That's what creates this horizontal component. It kind of takes a little practice. It might be confusing to see it that way, but if you look at it for a minute and you kind of tilt your head and you try to look at the vector, you can really see that that's what that component is. That's what the horizontal component is. It's negative I times sine of theta. And the y component, the vertical component, is just this j times the cosine of theta. because in this case, it would run that way, which is parallel to this. So it'd be j times the cosine of theta. So now that we know what these two things are, we can plug them in here and derive expressions for a of x prime and a of y prime in terms of a of x and a of y. So we can rewrite our vector, and this time we can write it with a of x prime times, instead of I prime, we replace it with this vector here. I times cosine of theta plus j times sine of theta, and plus a of y prime times this, instead of just a regular j prime. Doesn't really matter what you do. I try to stick with one notation, not confuse people. Usually this hat notation is used a lot, so I try to stick with it. But I kind of do things interchangeably. I'm a little bit of a scatterbrain myself, so let's see. Make sure everything is right. Alright, so that's this vector. All I did now was replace these things, the I prime and j prime vectors. So now what will happen is you'll get, if you rearrange these constants and these variables, you'll get I times a of x prime times cosine of theta minus a of y prime times sine of theta. Let me make sure I'm good with my space here. Plus j times a of x sine of theta, a of x prime times sine of theta, plus a of y prime times cosine of theta. So we have this and this. So now we have this form right here, because the i's and the j's are there. We were able to factor them out by algebraic manipulation. I don't want to go too deep into that. I'm assuming that you sort of understand how to do the algebraic manipulation needed to get from this point to this point. But what you should be able to catch is that this equation bears this structure here of there being an I and a j, and an a of x and an a of y. That means that this thing here must be a of x, and that whole expression here in the parentheses must be a of y. So now I'm going to clear the space up here, and I'm going to rewrite a of x and a of y. Clear up some space. Rewrite a of x and a of y. So a of x was a of x prime times cosine of theta minus a of y prime times sine of theta. And this ay was a of x prime times sine of theta plus a of y prime times cosine of theta. So now, I promised you in the beginning of the video that we were going to find what these components were. Right? That's kind of what we said. We said we already knew these, so why do we need an expression for them? We already know what they are. Well, what we can do now in order to get an expression for a of x prime and a of y prime is that we can change theta to a negative theta in an expression. And then we can just simply swap out the a of x primes with the a of x. Because really, if you sort of think about it for a minute, the way that we got to this a of x prime from a of x was to rotate it in the negative x direction. So really, in order to sort of get back to this, or get to this a of x prime, what we should do is just change the angle out to a negative instead of a positive. So everywhere where this angle theta, this normal angle theta exists, we'll make a negative theta. So that means that we should review real quickly what the sine and cosine of negative angles are. So we know from trigonometry that the cosine of negative theta is equal to just the cosine of theta. Negative and positive are the same. Now the sine of theta, negative theta, is equal to the negative of the sine of theta. So now with this information and what I just told you, we're going to replace theta with negative theta everywhere. And then basically all we have to do after that is everywhere where there's an a of x prime, you write an a of x, and everywhere where there's an a of y prime, you write an a of y, and the reverse for here. So once I replace these things, what will happen is this will transform into a of x prime being equal to a of x, because I'm just switching. Now the cosine of negative theta is equal to the cosine of theta, so I don't have to change anything there. And in this case, now the sine of negative theta, this will become negative sine of theta. So the two negatives will become a positive. Plus a of y times sine of theta. So now you have an expression for a of x prime. Sometimes I have a tendency to draw my y's so like, I don't know why I do that. Okay, so now we do the very same thing here. A of y prime is equal to a of x times negative a of x times sine of theta, right? Because the sine of negative theta becomes a negative sine of theta. So let me clarify that. Let me erase this and let there be no confusion as to what I mean. Okay, so we get negative a of x times sine of theta times sine of theta plus a of y times cosine of theta. So we accomplished our mission. What we sought out to do was to find the components of a vector in another coordinate space. So we started off with an original coordinate system in which we knew the components of a of x and a of y in that coordinate system. And then we said, hey, you know what? I want to find what the components of a, the x and y components of a and y are in another coordinate system that's very similar to the original coordinate system. The only thing that's different is that it's rotated by an angle theta off of the original coordinate system. And we said that as long as we knew that angle at which it was rotated at and the original components, a of x and a of y, at the original coordinate system, we could find the new components in that new coordinate system. And that's exactly what we did. And this is a very useful tool in analysis of physics, because a lot of times you'll want to look at things in different coordinate systems and coordinate frames that differ in this manner. And you'll have to take one vector that you know in one coordinate system and analyze its components in a different coordinate system.